Hi, this is Josh from Leet and in this video we'll be diving into the matrix and setting the values to be 0. Specifically, we'll be tackling the Leetcode problem, set matrix zeros, and building it from a naive solution all the way to the optimal solution. So it doesn't matter if you took the blue pill or the red pill, get ready to hack into the mainframe. Given an M by N matrix, if the element is 0, we want to set the entire row and column to 0. It's important to mention that we want to do it in place, meaning that we need to modify the existing matrix. So in the follow-up, we're going to figure out how to do this problem using m times n space, how to use m plus n space, and we're going to find a solution that uses constant space. So an example of this problem is we have this matrix right here, and we have 1, 0 in the middle, and because of that 0, all the columns and rows will also become 0. Let's see how we can solve this. So before we start talking about what works, I'm going to start talking about what doesn't work. When I first saw this problem, I thought to myself, easy. Let's just do a flood fill, which is a strategy that we used in the Counting Islands problem, which we did in the past. You can check out the video here. And we would basically fill in the rows and columns of the index whenever we encounter something with 0. So for example, we can just say we navigate through our matrix and we just keep everything the same until we encounter a 0. And then when we see the 0, we would just mark all of its columns and rows to be 0. So this would be 0, this would be 0, these would be 0. And then that'd be easy and we're done. While I was waiting for a rude awakening, when I moved to the next column where it is 0, but as you can see in our original input, it's actually a 1. The result of doing this, if we follow our algorithm, we would set the row above it to be 0 and the row below it to be 0, which then will lead us to the wrong answer. Now let's see how we can do better. Let's talk about a working brute force solution. The first thing we can do is realize that the problem says that our answer must be in place, meaning that we can't change our input. However, that does not mean we cannot use a copy of our exact same input as additional space to calculate our answer. What we could do is we could create an exact duplicate matrix, which we can reference to as we modify in place our existing matrix. We can iterate through all values in our matrix and see if there is any rows or columns that have a 0. In our first row and column, we can check to see if any of our rows or any of our column is 0. And if there is, we would just change our value to be 0. Now, in this instance, none of them are 0, they're all 1, so we don't change anything. However, once we go into the next column, we can check and we'll see that we do have 1, 0 in the row below it, but no 0 in the column surrounding it. But because we did find a 0, that means we're going to flip this value to be 0. So this would be 0, and this would just continue on, and we would eventually arrive at our solution. Now, it's great that we got an answer. We'll have a runtime of O of m plus n times m times n, which basically just comes down to O of m times n, because m plus n is just a constant. And our space-time would be O of m times n. Now, a follow-up question asks, can we do this? Can we solve this problem without using m times n space? Specifically, they hinted at m plus n. Let's see how we can do that. It was already given as a hint that we want to find an answer with a m plus n space. Now, how can we accomplish that? Thinking back to the matrix that we were using as space, we didn't really need to actually use all of the space that was provided to us. What was really important to note was that column 2 over here and row 2 over here had a 0. And thus, anything in these two, in this column or in this row, must be a 0. Taking that idea, what if instead of traversing through our matrix initially and making a duplicate, what if we just have 2 arrays of m and n, which in this instance are both 3, and one of them is used to keep track of all the columns, and the other one is to keep track of all the rows. And then when we run our algorithm again, we don't have to search all the rows and columns in the matrix, we just have to search the specific index of each column and row. So for example, when we first traverse through our matrix to create our column and our row, we would set the first column to be 1. The second column would be 0 because of this 0 right here. When we go through our row, we will set the first row to be 1 because there's no zeros. We would set the second row to be 0 because of, once again, this middle 0. And we would set the third row to be 1. With this, now we can do our in-place modification. We can go through our matrix one more time, and in every single slot, we will change the value to be 0 if either the row or the column has a 0, meaning that somewhere for that specific indice, there must have been another 0 in a neighboring column or a neighboring row. So going through this example again, we go to row 1, column 2. We see that there is a 0 in our column 2, so this will be switched to 0. In row 1, column 3, we see that they are both 1s, so we don't do anything. And just for one last time, in row 2, column 1, we'll see that row 2 actually has a 0, but because we only want them to be 0, we just switch this to be 0. And the pattern just persists, and we get our answer. This is nice in two ways because one, our runtime is now O of m times n, and our space now is m plus n because we are only using an array for our column and our row. Now at this point, you might be feeling pretty good about yourself and you think, yeah, I got the answer. What else do I need to do? Well, what if I told you there was a way to solve this problem in constant space? What? At this point, you might be thinking, how can we possibly solve this problem using only O of one space? I know, I had the same question too. But it turns out, what if we are changing our matrix in place while also using our matrix as the placeholder to figure out whether or not we should zero something out or not? It's crazy, but hear me out. Do we really care about the original values of the rows and the columns that we're switching? For example, if we knew that this column, column 2, is 0, does it matter if we preserve this column, row 1 and row 3? No, it doesn't. They can be 0, and we don't need to remember anything about it. Same thing for row 2. Improving upon our O of m plus n solution, we will use our first column and our first row inside our matrix as the placeholder. We would do the exact same algorithm what we did earlier, where we populated our column array and our row array. We would go through each of our element. We would set the values of the first column or the first rows to be 0 if there is a 0 inside that column or row. So for example, we at row 2, column 2, we have 0. So we would just go in place in our existing matrix while we are navigating it and just set this value to be 0 and this row to be 0. And then after we traverse through our matrix, we would go through our matrix one more time again just to fill out the zeros by checking the first column and the first row on every index. For example, we reached row 2, column 1. We would check and we see that row 2 has a 0, so we change this to be a 0. And we just continue on, and that would give us our answer. However, you might notice that there's a part 1 to this part, so there's an edge case that we haven't thought about. What could it be? Let's find out. Here's another matrix that we have. The only difference here is that we have a 0 in this space right here. If we were to follow our previous algorithm, where we would set the first column and rows, we would set this indice to be 0, and this lays our problem. We didn't define what it represents. Is it 0 for the columns, or is it 0 for the rows? If you recall, in our m plus n solution, we have a 3 by 1 and a 1 by 3 array. And each of them has their first index, so we would know if we're referring to the column or the row. So how will we rectify this situation? Well, one very easy way to do this is we will just simply set two new booleans, row and column, that will be used to indicate whether or not we should fill the whole row or not. So in this example, because our 0 is in row 1, we'll set this rule boolean to be true. Continuing on, we'll move to our second 0, and then we will set the appropriate 0. And now that we have set all the circles, we can go back to our initial algorithm. The first thing we'll do is we'll mark all of the indices that's not part of the first row and column, because if we do that, we would have the same problem we had with the flood fill. We don't know if we set it to be 0 or it was originally 0. So the first thing to do was we will switch. So only looking at starting from our second row and column, we would start right here. This is already 0, so we don't do anything. On row 2, column 3, we know that there is a 0 already, so we can change this to be 0. On row 3, column 2, this is already 1. We know that on column 2 there's a 0, so we just set this to be 0, and that's about it. And the second part of this is if our row or our column is true, we'll set everything in our first row or our first column to be 0. So in this instance, because row is true, we will iterate through all of our values in our first row and set them to be 0. And this would give us our answer. Now let's get to the implementation. To start off, we always want to make sure to check our edge cases, which in this instance is if our matrix is empty. Now we need to create 2 booleans to indicate whether our rows or column needs to be filled. The first thing we need to do is we need to go through our matrix and change the first row and column in place to tell us whether or not we need to fill the whole row or column. If the current index we're in is 0, we need to first set our first row and column to be 0. So we'll remember to go back and finish it. And if our I or our row or J, our column, is 0, we need to fill the whole row or column. And we use the boolean to remember that later on. Now, after we marked our placeholder to fill in the rows and columns, we'll start going through our matrix to set everything to be 0 if there's a corresponding 0 in the column or row. It's important to note that we start at I equals 1 and J equals 1. We don't want to fill in our first row and first column just yet. Now, after we set everything except for our first row and column, it's time to set it. If there was a 0 in our first row, we need to 0 out our first row. Likewise, if there's a 0 in our first column, we need to 0 out everything in our first column of our matrix. And that should be all we need to do to solve this problem. Let's run the code, figure out what. Awesome. And if we submit the code, and there we go, we have the answer. And there we go, that's how we would solve the set 0 matrix problem. To recap, to solve this problem, our brute force solution was to duplicate the matrix, and then for every index as we navigate through it, we would just check all the rows and columns that's associated with each of our indices in our matrix. We can improve upon that by realizing that we only care about the row and column indices, and we just store these values in a smaller row and column array, which would give us the same runtime, but it would give us a spacetime of O of m plus n. And finally, to achieve constant space usage, we can use the same strategy, except we can store the values in our existing matrix. If you found this video helpful, please hit the like button. And if you really like these type of content, consider hitting the subscribe button to get weekly content updates. And in the meantime, consider checking out some of the other videos that we have over here. Alright, that's all. Have a nice day.